Okay, in Microlecture47, we're covering the second alkene addition reaction, which is acid-catalyzed hydration. Okay, so the next reaction is this addition of dilute H2SO4 to alkanes. And one thing that you're going to notice is that it is indeed a dilute solution of sulfuric acid, not like the concentrated sulfuric acid that we've seen in a different reagent set with E1 reactions. All right, so you'll definitely be able to tell this reagent set from that reagent set because of this dilute factor. All right, for these reactions, we want to be able to, again, predict the regiochemistry, and let me fix my copy-paste typo here. It shouldn't be where X adds to now, it's where the OH adds to for this set of reactions. So when we're using a dilute solution of H2SO4, we're effectively adding a hydroxyl group, an OH group, to one carbon of the carbon-carbon double bond and hydrogen to the other. So we're adding water across the double bond. So regiochemistry is important, and also stereochemistry. So if the product is chiral, then we have to be careful about how we represent the product in terms of how we draw it having dashes and wedges and so on. All right, so the reagent itself, notice it can be written out this way, dilute H2SO4. We could abbreviate a bit and say dilute H2SO4 that way. It also might be written H2SO4 and water. All right, so any of those forms is acceptable. Let's do a few examples here of different alkenes, and just kind of predicting products here. We'll go over the mechanism next. All right, so we think about both sides of the carbon-carbon double bond here, and we see a more substituted side of the carbon-carbon double bond, and that's the side that's going to pick up the OH group. The other side is going to pick up the hydrogen. Again, we don't have to draw that hydrogen in, or you might draw it in just for clarity. We've effectively added water across the carbon-carbon double bond. Okay, there is no stereocenter here, so we can draw this way. It's achiral, and so we can keep all the bonds planar, like drawn on lines, with no dashes and wedges, because it has no stereochemical consequence to this reaction. So the next one, regiochemistry would dictate that the OH group adds to the more substituted carbon. So OH would add here. There's also a methyl, there's also an ethyl, so a lot going on that carbon. The hydrogen atom adds to the other side. You may choose to leave that off, which is perfectly acceptable. But we do see a stereocenter. And so we need to be able to draw both forms that would result. It's going to be a mixture, okay, but we have a chirality center, and so we want to be able to indicate that we've got a situation where OH is pointed forward and the methyl back, and we've also got the situation where the OH group is pointed back. Okay, it's a 50-50 mix of enantiomers, and so it's a racemate, and so the product is achiral. Right. So whereas we would predict the product of the first reaction in such a way that we could just leave bonds on lines, we would want to predict this product to show that both enantiomers form. It ends up being achiral because we have a 50-50 mix of enantiomers. The next example has a benzene ring, and I just really want to point out loud and clear that the benzene ring is not an alkene, right? And so that's never going to react like a carbon-carbon double bond. It's not going to do any of these reactions. So never react benzene in any of these chemistries that we're doing. It's a very stable part of the molecule. And so the only part that reacts is the isolated carbon-carbon double bond on the other ring. And we're going to see some regiochemistry here. The OH is going to go on this carbon atom and not the other carbon atom. So we'll cover the mechanism on the next slide. We are seeing a stereocenter, right? And so we would want to predict that the OH group is going out of the plane just as much as it's going into the plane. In other words, we have a 50-50 mixture of enantiomers that form. It's a racemate, so it's achiral. So my note here applies to both of these reactions, this one and this one. So let's think about the mechanism details. We'll use the example, the last example there, to draw out our mechanism. So we know that we have a dilute solution of H2SO4. What that means is we've got H plus and we've got water. Okay, that's what that means. And so the double bond is a nucleophile. H plus is a good electrophile. And so we pick up H plus across the double bond. And H is going to end up over here in this case. And my plus charge ends up here. Okay? So just like the first step of HX addition to a double bond, works the same way. H is going to add to one carbon, and the other carbon is going to be a carbocation. Take a moment here and think about why I didn't do it the other way. So I didn't place the carbocation on the carbon atom farther away from the benzene because I would have less resonance stability there. So here I'm seeing lots of resonance stability, and so whenever you can make a more stable carbocation, always do. So this is the resonance stabilized carbocation. The other carbocation therefore would not form. All right. And so after this carbocation forms, I've got water in solution, and the lone pair of electrons on oxygen can go ahead and attack at the site of the carbocation. And so now I have this intermediate with positive charge on oxygen. We're almost to product. We just need to deprotonate that alcohol. All right, and so that takes place using a conjugate base from solution. We can deprotonate and form the final product. Okay, which looks like that. Now, the reason why we want to show the possible stereochemical outcomes is that we have this chirality center here. All right, so we have a chirality center. We want to be able to show all the possibilities, and what it comes down to is that this water can approach from the top face, or we could have approached, from the bottom face, the other side, with equal likelihood. Right, so attack could have happened from either top or bottom with equal likelihood due to the fact that carbocations are flat, they're planar. And so for that reason, the OH group in the end might have come from this side or this face, leaving us with this product, but equal likelihood the OH came from the back face, leaving us with that as a product. So our final predicted products will look like this. Keep in mind too what we know about reaction kinetics, and that we could pick out the slow step of this reaction. which is the slowest step. We would call that the rate-limiting step. And that's always going to be the formation of the carbocation, remember. And so I see that carbocation forming in this very first step when we pick up the proton. So this is going to be the slow step, and all subsequent steps will be faster than that first